Hello, and welcome to another episode of the Storytellers podcast. In this episode, I was lucky enough to talk to an Australian Nobel laureate by the name of Peter Doherty, who won his prize in the field of medicine. Peter and I had a fascinating and very useful discussion, I think, centering on the theme of Covid-19. Before briefly touching on the nature of his award, which has relevance to the discussion at hand, we went over what COVID had been up to this point, and where we currently stand, and also what the future potentially holds. We talked about vaccine hesitancy amongst the population, and we also talked about the current state of vaccine efficacy, which I know is a question that looms large in the eyes of many. We also talked about long COVID and the current state of long COVID, just how real it is, how much of a COVID-induced phenomenon it is. And we also talked about Peter's perceptions of our responses to the COVID-19 pandemic. And to cap things off, we talked about briefly the Doherty Institute, named after Peter, which performs vital medical research and examination. This was a great conversation, and one that I think many will find quite useful and informative. I know that a lot of us have fallen into a bit of a lull when it comes to our perceptions of COVID and its relative importance in this moment, but it is still yet present and may still rear its head again in the future, though we may think it to be a past problem. Anyway, without further ado, I give you Peter Doherty. So, today I have the honour of speaking to Peter Doherty, an Australian medical icon who has quite the set of accolades to his name, and it seems rightfully so. Professor Doherty is a Nobel laureate in the field of medicine, has won the Paul Ehrlich Prize, the Gardner International Award, and the Lasker Award. He has been awarded more than 20 honorary doctorates and published over 500 research papers. He was Australian of the Year and is a companion of the Order of Australia. So, Peter, thanks for talking to me today.
Yeah, it's a pleasure, Lucian.
Cheers. So, just briefly, would you perhaps be able to tell us what you won your Nobel Prize for, just as a bit of an introduction, and what your sort of background has been up to at this point?
The Nobel basis of the Nobel Prize was a discovery that we made almost 50 years ago next year. And what we discovered is that the transplantation system signals to the immune system that something is wrong with the cell and arranges basically for the cell to be destroyed. Now, I'll expand on that a little bit. As you all know, if we graft a kidney from one person to another, unless we're identical twins, it will be rejected. And that's because we have a very different spectrum of proteins on the surface of our cells. Each individual is different. And if they are recognized by the immune system if an organ is transplanted from one individual to another, and a response called the T cell response or killer T cell response turns on to reject that transplanted organ. So there's no obvious reason for us to have that system, except perhaps to reject, say, a tumor that might be passed by a handshake or something of that sort, which is rather unlikely, though we do have a situation in the Tasmanian devil where a cancer is transmitted by biting. So why do we have this transplant system? Well, it turns out it's not really there to reject organs from other people, which doesn't happen in nature. You need a transplant surgeon to do that. It's basically there because when it's changed in our own cells, it tells our immune system that cell is damaged or dangerous and must be destroyed. And we discovered this through virus infection, where in a virus infection, very small bits of the virus are carried to the cell surface by the transplant molecules. And it's that change to those molecules that's that's seen as foreign and leads
Mhm.
to the cell being killed. And with a virus infection, viruses can only grow within our living cells. So you have to get rid of those factory cells, and that's what this does. And the same principle applies to rejecting cancers, and it's being used in cancer therapy and various other things. So it was a very big discovery made from some very simple experiments, and we wrote a theory around it, which I've just about principally basically outlined to you, with a lot of other features to it that are of interest to immunologists. And that's what got us the Nobel Prize 22 years after we published our findings. And that Nobel Prize is now 26 years ago this year. So one thing that is certain is it makes me very old. I'm actually what I describe as part of the living fossil record of my subject, which is immunology.
Well, it sounds like very foundational research. It's interesting that you were awarded the prize so late after the initial work.
That's not a long time for a Nobel Prize.
Right.
The actual Nobel, the rules that Nobel set out, and Alfred Nobel was a manufacturer, a chemist. He made dynamite, I think, or nitroglycerin. He thought that explosive was so terrible when he discovered it in 1896 that it would end all wars. He wasn't quite right.
Yeah.
But when he died without children, and he left his estate to set up the Nobel Prizes, and the Nobel Foundation took it over. And the first prize was awarded in 1901. These are all basic prizes that are directed at what he considered the higher activities of human beings. And he considered science very high on that list. So there's a Nobel Prize for physics, there's one for chemistry, medicine, and one for literature. Later, the Swedish banks added the Swedish Banks Prize for Economics in the name of Alfred Nobel and bought their way into the Nobel system to offer an economics prize, which was very welcome because they paid a lot of money, which gets put back into the amount the prize winners are given. And there's also, under Nobel's will, he established the Nobel Peace Prize. Sweden and Norway are at that time together, and he gave the Norwegian legislature the job of awarding the Peace Prize, which is often highly political. The science prizes are all awarded by various specialist committees or recommended by various specialist committees that meet in Stockholm, as is the Literature Prize, which can be political also in one way or another. And they tend to be pretty apolitical.
Sounds like classic economists, hey, buying their way into a prize for themselves.
Well, economics is a very important field, but whether you call it a science or not, it is called the dismal science by some. But anything that deals with human behavior is very difficult, as we know.
Yeah. I had a conversation with Steve Keen. I'm not sure who you may or may not be aware of, Australian economist, some time ago, and he was quite disparaging of the field and definitely would not think of it as a science. But
well, it's we need them, I guess.
Yeah, we need them to some extent,
and we need them to be sometimes a lot smarter and to show a lot more integrity than some of them actually do.
True.
Some of them are great. I mean, I'm not disparaging economists en masse. Ross Garnaut, for instance, wonderful Australian economist.
Yeah. Okay, we'll leave economists alone for the moment.
I think so.
Get on to topic, which is COVID-19, which I know you've had some things to say about in the past on various other podcasts and platforms and whatnot. So I was wondering if you might just, for us, be able to summarize what COVID has done up to this point, how it is sort of manifested up to this point, and what it is doing in this moment.
Yeah, basically, we knew that there was a real threat out there. We've known for some time now that bat populations are carrying a lot of different viruses. We didn't know this before the year 2000. If you'd asked me, I've been involved in this field, infection and immunity to do with viruses now for Next year will be 60 years.
Mhm.
If you'd asked me if bats carry any viruses that are a threat to humans, I would have said they carry rabies-like viruses, rhabdoviruses, and transmit them by biting. And you don't want to be bitten by if you try and catch a fruit bat, for instance, you may get bitten. And you could get a rhabdovirus infection, a rabies-like virus infection, even in Australia, though we have no rabies virus. And in fact, Australian licensed bat handlers are all vaccinated against rabies. So we knew that. But apart from that, we knew no virus is transmitted by bats. And then along came the SARS virus of 2002, 2003. And then we had Hendra and Nipah virus in horses and pigs in Southeast Asia. Worked on a lot at the Australian Animal Health Lab in Geelong. And people started to study what's in bats using new technology, particularly deep sequencing type technologies that are exemplified in the work of Eddie Holmes at Sydney University, a wonderful scientist. And the work on the paramyxos, the Hendra and Nipah, we call them henipaviruses. They're a subclass of what we call paramyxoviruses, which cause croup and so forth in kids. They were worked on very extensively early on by Linfa Wang, an Australian-Chinese scientist at the Australian Animal Health Laboratory, now the Australian Centre for Disease Preparedness or something at Geelong, a big high-security lab. So we now know that bats carry an enormous spectrum of potential pathogens that can infect us. A whole lot of coronaviruses, paramyxoviruses, filoviruses. These are the viruses that Ebola belongs to, Marburg virus, and that they transmit to us, often via an intermediate species. So the first of these that really bothered us was SARS in 2002, 2003. The first SARS, 8,000 people in all became infected. It was a more lethal virus than COVID-2. It killed about 10% of the people infected, but again showed the same profile of being more lethal for the older people. And but it burnt out. So then two more common cold ones were detected for the first time in 2005, one in Amsterdam, one in Hong Kong, both cities that have big international airports. Then along came MERS, Middle Eastern Respiratory Syncytial Virus, which goes from bats to camels to people. And that infected and killed people in the Middle East, got across into Thailand for a bit, but hasn't spread very much. Kills about 30% of the people it infects, and but doesn't infect lots of people. And then in 2019, along came COVID-2. And it's the worst of the lot because it has an ideal characteristic for a pandemic pathogen in that many of the people who become infected don't become very ill, mainly young people, at least not initially. And the people who die are older people and people with defective immune systems due to one reason or another, or other diseases like diabetes. It's highly lethal for diabetics, for instance. So it's become an extraordinarily dangerous and unpredictable pathogen. And not all of us underrated it at the beginning, quite frankly, when it hit in the beginning of early 2020. So we were saying at that time, this is not influenza, but basically we were thinking of it like influenza, like a respiratory virus that spreads very rapidly, and that we thought that it would be like influenza, that the 1918-19 influenza pandemic was much more lethal than this. It killed 50 million people in a global population that is about a quarter the size of today. Okay, they're highly lethal, killed enormous numbers of people, and but it was over in just over a year. Really started really being serious in the latter part of 1918. It didn't get to Australia till 1919. It had already weakened a bit by then, and by 1920. People weren't worried about it. We're still worried about COVID-2 3 years later, almost 3 years later. So this is a very different pathogen. And there are many other features to it, which I can elaborate on.
Okay, so why is COVID something that we're still worrying about at this point? It appears to me, just from the ground, from a casual, common perspective, that COVID has disappeared sort of into the background, at least in terms of in people's. It's not front of focus in many people's
It's still
minds.
infecting about 60,000 and reported cases, and I'd say reported cases now in the United States are probably about 50% of cases, about 50% probably not reported. It's still infecting 60,000 reported, still 60,000 reported cases in the USA. Numbers have fallen down here, but this is BA5 Omicron. I think Victoria still probably about, about 10,000 cases a week or something. I'm not sure. I mean, it is falling. The BA5 numbers are falling. So we've got people who've been vaccinated 3 or 4 times. We've got people who've been super infected after vaccination because the vaccine is now too distant from the virus. The vaccine is against the original 2019 Wuhan strain, and the virus has undergone multiple mutations. So what we underrated with this virus is its capacity to mutate and still infect without suffering what we call fitness cost, which diminishes transmission. And so we had no idea that it would be so serious in that respect. So what we're waiting for now is Omicron looks a bit less severe, but you're not really quite sure that's true because people have had multiple vaccines, which are tending to protect against late-stage disease still. And that's working through the T cells, the stuff we got the Nobel Prize for, not through the antibody response, which is the normal protective response stimulated by vaccines. So Omicron is killing less people, and it put less people in hospital, but people are heavily vaccinated, so that may be part of the reason. We also have antiviral drugs that work that have been given to the elderly, particularly Paxlovid, so that will be saving a lot of people. And the level of reporting has fallen right off. The governments were paying an enormous amount across the planet to do PCR tests and have very widespread surveillance for this virus. That funding is all gone. And so we're not sure we're getting a real perception of how much virus infection is out there. What is really the benchmark is how many people are coming into hospital sick with this virus. And at the moment, it does look better than it has been. There's a variant spreading in India called BA2.7.5. It's been detected here. It hasn't taken off. And it's thought, again, that it may be less virulent, but quite frankly, we don't really know.
So not only is the virus becoming less prevalent, but it's becoming less severe in terms of
not that clear. It's all that less prevalent. It is BA5 is dropping off. What we're worried about, of course, is another different mutation that'll come roaring back in.
Okay, right. And
if you look at the family tree for CoV-2, the variants we heard about, alpha, beta, delta, okay, were all separate mutants that came off at different points. Okay, so they're what we call subclades, and they were independent mutations. They weren't related to each other any more than they were related to the original virus.
Right.
But Omicron has established a lineage. So what we've been dealing with since late last year is the Omicron lineage. And now we're up to BA5, and we're just coming to the end of BA5. It's quietening down. Now, whether there will be another virus that comes on later or not, we don't know. There's no particularly obvious sign of a newer variant or even an independent variant, which is spreading a lot anywhere. But we don't know that won't happen. Right. We hope it doesn't. We hope we're coming to the end of it, but we don't know.
Okay, well, this was going to be one of my later questions, but I suppose I'll ask it now as it's on topic. So basically you're saying we're not sure what the future is going to look like, basically.
We've become pretty careful about predicting. because we've been wrong, and we underestimated the capacity of this virus to change as rapidly as it and effectively as it does. It, normally, when a virus changes, it has to change. For the virus to change and escape from the antibody response, it has to change what we call the receptor binding domain of the spike protein, which is one of the proteins on the surface of the virus. And it's been able to change that receptor binding domain in ways that we thought would make it less fit, that it wouldn't affect as much, that it wouldn't spread as much, but it hasn't necessarily made it less fit. And so that's basically a bit the conundrum we're in. So we'll see what happens. I mean, basically, that's what we're doing, is waiting to see where it takes us.
Do you think it's... Do you think...
Sorry, it's kind of instructive that with the enormous sophistication of modern science, and it is enormously sophisticated, in 1918, 1919, we didn't actually isolate the influenza virus. We didn't isolate any influenza virus until 1931, I think it was, 12 years later. Okay. With COVID-19, the virus was first detected in China about December 2019. And by January 2020, mid-January 2020, the sequence of the virus was published. If someone in 1919 wouldn't have even known what you're talking about if they talked about a virus sequence, because they had no concept of a gene sequence. The sequence of the virus was published in mid-2020, mid-January 2020. We had a diagnostic PCR test based on that sequence within 5 days, and diagnosed the first case that came to Australia in Melbourne in, I think, January 24, 2020, with the PCR test. And the vaccine manufacturers were starting to make experimental vaccines from mid-January 2020.
And would you be able to speak perhaps to why so many people in and outside the academic community, it seemed, were skeptical and suspicious and cynical of the rapid pace at which
I don't know if there was that much skepticism. I'm not sure which academic community, and the academic community is a big family. It covers everyone from historians to even economists and certainly medical scientists. But I think within the informed medical community, there wasn't great skepticism about the vaccines. But basically, the problem with vaccines is, and we've seen it, I don't know if you saw the movie Contagion.
It's been on my list for some time, I think.
Yeah, you should watch it because, it's based on the original SARS pandemic. And Gwyneth Paltrow basically gets the virus from a chef who gets it from a pig who gets it from a bat. And then Gwyneth Paltrow comes back to the United States, and anyone who comes within about 10 feet of Gwyneth Paltrow catches the bloody thing and probably dies. And Gwyneth herself eventually dies. Not the real Gwyneth, a fake one. Thankfully. They take the top of her head off. I think it's a dummy, not a stand-in. And so that we see the post-mortem. But then, they isolate the virus, and then within about a week, they have a vaccine. So that's where the movie kind of falls apart, because we've seen what happened with the vaccine here. The problem with vaccines is you have to be sure they're safe. And so an enormous amount of testing was done. It has to go through what's called a phase, has to go through what we call preclinical studies. That is, you have to inject it into animals, see if it works and makes an immune response and protects animals against virus challenge. Then you have to do a phase 1 clinical trial, which is a small trial in humans, where you just have to be sure it's safe. Then you do a phase 2, phase 3, where eventually you put it into hundreds, maybe 100,000 humans, and see whether it's safe and whether it works. That takes months. And then the only real trial, of course, is when you start to put it into millions of humans. And that's what's called the phase 4 trial, which is basically rolling the vaccine out. Now, what happened with the vaccines was China made a very conventional vaccine, which is a formalin inactivated vaccine, or a beta-propiolactone inactivated vaccine, much like the flu vaccines we used,
Mhm.
that hasn't proved to be a particularly good vaccine. It was made against whole virus that was
Mm.
killed. You grew up the virus, then killed it. That's the way we make flu vaccines,
Mhm.
with a bit more sophistication than that, but not a whole lot more. But the British made what we called adenovirus vectored vaccine. They used a virus called a virus that infects chimpanzees, actually, causes respiratory infection in chimps. They engineered that virus to put in the DNA. It's an RNA virus, but you make a reverse copy and make DNA. The DNA for the CoV-2 spike protein, so that it's actually delivered to, as a vaccine. What you're giving people is what we call a defective adenovirus that can't go through a further cycle of replication, but can get into cells and express the genes, both of the adenovirus and of the spike protein that's been loaded into it. Now, that vaccine was working reasonably well. It was the AstraZeneca vaccine, or Vaxzevria, but then it was found that a small proportion of women, particularly, were being killed by this thing. And so, that's part of the story of vaccination. It's a risk-benefit equation. And some women died, a very small number, but you can see it on the Therapeutic Goods Administration website. Look at our TGA website, and it will report to you exactly what happened there. And of course, that vaccine was withdrawn, though it's used widely in many, many countries, because the risk-benefit in a country where the virus is circulating at a high level is much in favor of being vaccinated. We weren't having much virus circulation at that stage because of the lockdown. Then with the mRNA vaccines, there's a different strategy, but again, you're actually delivering the molecular template for making the viral spike protein. So the adenovirus vaccine strategy had been around a long time. Certainly, we could have made a COVID-1 vaccine from it early in the 2000s, and it had been used as an Ebola vaccine made in that way, had been used to limit Ebola outbreaks in Africa, and was quite successful. But it wasn't injected into millions of people the way the COVID-2 one was. The mRNA vaccine was completely new to humans, so that got a lot of people upset. They were worried about it. They thought because it says RNA, mRNA is actually a template for making protein. You don't copy mRNA back to make RNA and then DNA, but people were worried it could somehow get into our genome, and some of them still are. So that was totally revolutionary. It has a problem too. It can cause myocarditis and pericarditis, particularly in adolescent males. Sometimes they have to be hospitalized. Sometimes there are long-term consequences, but in the main, the cardiologists say it's easily handled and they're okay. And of course, the thing about COVID-2 is it's much worse at causing all these problems. The blood clotting problem was apparent with the AstraZeneca vaccine, and the pericarditis, myocarditis we saw with the mRNA vaccine. The virus itself does both things at a much higher level and much worse.
There's a few people I was following throughout this time, one of whom is Nicholas Christakis, who's both a physician and a sociologist, and I don't believe a virologist, but has done some work in that field. And he made the point that vaccines, because there was, I suppose, a lot of perhaps misapprehension around these vaccines and what exactly they do and how you should sort of conceive of them. And his example that he put forward was as the vaccines effectively being a seatbelt in a moving car that was about to crash, with that car being COVID in a sense. And
I've used that same analogy, actually. I mean, basically any medical intervention is a matter of relative risk. So, I mean, people like me are trained to look at the world through a prism of probability and relative risk. Okay. I mean, I live near a busy street across from Melbourne University, which has trams and 4 lanes of traffic and stuff. And the probability that I get into trouble if I cross against the light is much higher than if I stay on the footpath and wait for the light to change, even though the probability then is not zero because some maniacs come through red lights. But we do a relative risk assessment. We do that all the time
Mm-hmm.
in situations like that, crossing the street. And wearing a seatbelt is a relative risk assessment. Sometimes, if you've got a seatbelt on, it can make the accident worse. It can happen. But in most accidents, you're much better off if you've got the seatbelt on. And most people understand that, I think.
Mm-hmm.
So we think of probability and relative risk in those sort of terms, but we don't think of them in terms of things like vaccines. But no matter what you do, just sticking a needle in someone has some risk.
Mm-hmm. Yeah, risk to the arm.
I mean,
I
had a, and you can't, anyway, there's all sorts of weirdness about this. I mean, a friend of mine who's a virologist, really pediatrician and virologist, his wife is a pediatrician. And he describes how she's got a baby in her office, and she's about to give the baby the standard vaccine dose.
Mm-hmm.
And the baby goes into convulsions.
Mm-hmm.
Babies do that. They regularly fit. They're usually okay, but it's not uncommon in small children. But of course, if she'd been injecting the vaccine, that would have been responsible for it. But she wasn't. I mean, she wasn't anywhere near the baby. So there's a lot of issues about the fact that vaccines are tied to something. I mean, people will link some sort of adverse event to a vaccine if it happens a month or 2 months later.
Mm-hmm.
So you get what are called adverse events reports, which are very large numbers of these, because if you vaccinate, say, 1 million people, and you go across the age range, in the next month, some of those people are going to die. Some of them are going to develop another problem, and some of them are going to get worse with the problem they've already got. So there's a tendency to think that if they've been vaccinated, and this happens within that next month, the vaccine caused it.
Mm-hmm.
Okay, so a lot of the people who are against vaccination just look at the adverse events reports. There's large numbers of adverse events reports. You don't need to justify anything. You can do this as an individual. Your doctor can do it, or whatever. You can put in a report to an authority like the Therapeutic Goods Administration. So what then the professionals at the Therapeutic Goods Administration have to do is to screen through those adverse events reports and say, oh, this one looks like investigating, because we think this is a known problem with this vaccine, and so we'll investigate this. And then when you do that, you'll find actually, though a lot of people looking at adverse events reports will tell you that the mRNA vaccines have killed a lot of people. In actual fact, I don't think they've killed any Australian.
Is that right?
I don't think so. You can look at the TGA report for yourself. Look at TGA adverse events reports. It updates every couple of weeks, I think. And you can, I mean, if you're sending out information, send out the link.
Well, I suppose what you were speaking to there was our propensity towards a negative a bias of disproportionately weighting those adverse events, and whilst ignoring those events that were not adverse.
Well, it's all very natural, I think, and people don't normally think in this kind of context. But that's the way scientists think.
Well, hopefully. Think.
And it is basically biomedical science, particularly, and doctors. You think in terms of relative risk. That's the equation that a doctor will always go through before they use the therapy. And for the Paxlovid is a good case in point. The drug, the antiviral protease inhibitor, it's got the Paxlovid is an anti-coronavirus drug, so it knocks the coronavirus. It doesn't kill it, but it stops it multiplying. So basically, cells, you've still got some infected cells, potentially, but the virus is not multiplying through the time you're taking this drug, which is 5 days. After you stop taking it, you can get a relapse, which I did, when I had it. And it's very common with older people, but the virus then soon cleared. But along with the anti-coronavirus drug, which is specific for the coronavirus, there's another drug called ritonavir. Now, ritonavir is a drug that's used in the AIDS cocktail, and what it does is it stops the enzyme that will break down protease inhibitors. Paxlovid is what we call a protease inhibitor. It blocks one of the virus molecules that's necessary for the virus to multiply. So ritonavir stops it being broken down. and that gives you higher drug levels for longer. But it will also do the same for other drugs that are normally subject to this type of control. Some of these statins, for instance, that are used for blood cholesterol medication, some of the blood pressure meds, if you give people who are taking those ritonavir, you will prolong blood levels and you will get an over-the-top effect. So a doctor has to make a relative risk decision when approving Paxlovid for a patient. If they're taking these drugs, they have to say either, oh, you must stop taking drugs A and B, or they may think, well, you're at such risk of the problems they're holding at bay, we're not going to give you Paxlovid. Okay. So that equation is constantly in the head of a physician who's administering drugs, for example.
Right. So, okay, so just to perhaps backpedal a little bit, would you be able to speak to, you've touched on it briefly, but speak to the efficacy of our vaccines going forward and the, let's say, well, the relative benefit of getting vaccinated at this point?
Look, honestly, we're still trying to work this out. Firstly, the vaccine efficacy has fallen right off. The vaccine worked against the original Wuhan strain, tended to limit transmission. By the time we got to BA5 Omicron, the antibodies are no longer working very well at all because they're too distant. And you're not stopping transmission. It's pretty hard actually to stop transmission anyway. The antibody molecules, which are Y-shaped molecules that float around in blood, grab hold of the virus and block it from binding onto our cells. Those antibody molecules, it's easy to keep them at high levels in blood. The cells that are making them, they're called plasma cells, are sitting in our bone marrow and pumping this stuff out into blood. But when it comes to keeping them at a high level up here in the nose, which is what you've got to do to stop infection, it's really low. And basically, it's a dating game. You've got the virus coming in that's got a receptor for some of the cells in our nose. You've got antibody molecules that can block that. But, the dating game is in favor of the virus interacting with the cell first because there's not a lot of antibody there. If we could flood the nose with antibody, great, but we can't. I mean, you can't just blow it up the nose. It'll just come out in mucus. And there are some strategies like intranasal vaccines, which are being tried now in combination with traditional vaccines to try and get more antibody production up here. That might help. But at the moment, the vaccines are too off their target. So the vaccines are actually working through T cell response, which that hasn't changed so much with the vaccine. So the first question is, it's shown us, COVID has really shown us the limits of vaccines. It's also shown us that vaccines that stimulate T cells could be useful, and we could go further with that. So that could be a new strategy for vaccines. There's been a lot of work, a lot of thinking about how we make much more cross-reactive vaccines. But that thinking's been going on now for decades with AIDS virus and with the flu viruses. And nothing has really come through that actually is great. Maybe this will drive that further forward and we'll do better in making highly cross-reactive vaccines. I think we'll think in those terms. And maybe we could try and work out how we get vaccines out there a bit quicker, because we've really been pretty slow at getting them out. And the other thing is that with COVID, we've done things we've never done before. With adult human beings, if we do vaccinate them yearly, we just give them one shot, say of a flu vaccine. We've never gone ahead and given adult humans 3 or 4 doses of vaccine in quick succession. That's never been done. And, we're just starting to try and understand, as a lot of experiments have been done or in progress, the analysis is being done. They're really pretty complicated experiments to actually evaluate what's happened here. But we've been doing whole experiments in the human population we've never done before.
So how concerned do you think, or should your average citizen be about COVID at this point? How much should it be on their mind as it was?
Well, honestly, I think if you're older, you still should be really concerned and protect yourself. But, I got it and people are getting it. It's very infectious. I think I'd try and avoid getting it more than once, because there's indications that getting it more than once can make it worse. And with younger people, there's always the risk of long COVID too, which again is another complex we're trying to understand.
Could you speak to that, perhaps? What could you speak to that, perhaps? What we know about long COVID at this point?
Well, there are various forms of it. You get a long sequel after a virus infection, and you seem to have recovered, but then your health is not as good as it should be, or you're getting, and with long COVID, you get brain fogs, you get muscle pains, gastrointestinal pains, reduced exercise tolerance, very common. People who've been athletes now actually find it hard to walk 100 yards.
And we're sure that those symptoms can be attributed to COVID.
Oh yeah, absolutely. They're all the studies of long COVID are all linked to an initial PCR diagnosis. The systematic studies that are going on. Not all the reporting of long COVID, because a lot of the reporting of long COVID is self-reporting. But the studies of long COVID that are being made very systematically, where people have been diagnosed and then they're being followed for months and maybe years, all of them start with a positive diagnosis. Often they were fit young adults. These are the ones that are particularly concerned. So the problem with long COVID is it's a very amorphous distribution. One component that many still consider to be long COVID is what we call PICS, post-intensive care unit syndrome. This is people who got very sick, had to go to hospital, were on a ventilator. Now, anyone who's in that situation can suffer a lot of tissue and organ damage, which may not repair. And we know, for instance, that though people apparently recover after that event with influenza, they may well die much earlier, for instance. So you've got to take that PICS component out. The people who got very, very sick with COVID, went to hospital, were on a ventilator, and they just survived. But then there's this other cohort of long COVID. This is the worrying one. These are people who often have a very mild, even an almost subclinical infection. They're fine, and then about a month later, 3 or 4 weeks later, they start to feel dull, drowsy, and they can be compromised for months. And in some cases, it seems to be getting worse. Now, we've always had this syndrome around with what we call myalgic encephalomyelitis chronic fatigue syndrome, which has been a very, very difficult disease for physicians to handle, because often they do all the usual blood workups and everything, and nothing looks wrong, but you can see the patient's sick. And then they're unwell, and there's been a tendency, it's more common in women, there's sometimes been a tendency to say it's psychosomatic, whatever that means. But basically it's a real disease. So I think long COVID is very similar to this, but it's following COVID-19. And basically this is the problem in young people. And this could be, we don't really know the incidence because a lot of it's self-reporting. But, at the acute stages of it, it could be up around 20% of people. And in the long term, it may be 2 to 3% of people or more. We don't know. We will know, but it will take time.
Taste seems to be a common affected
taste, not so much with the with Omicron as earlier on. The viruses vary a bit in the type of infection they cause. But the other thing we didn't know when I said we said it's not influenza, but we thought about it like influenza, is influenza is not what we call a systemic disease. That is, influenza virus gets into the respiratory tract, and that's where it multiplies. It doesn't go around the body in our blood. It stays out of the blood, actually. So it can cause damage by what we call cytokine storms, where you produce a lot of toxic molecules in an attempt to get rid of it. And those molecules get into the blood and they make you feel sick, and they interact with receptors in your brain. They make you feel sleepy. This is a normal process of an infection. In fact, you get a bit of it with a vaccine. The vaccine, it mimics an immune response. So the vaccine gives you a sore arm for a couple of days. You may feel drowsy. You may feel like crap for a couple of days after a vaccine. Perfectly normal. Nothing to worry about. If it goes on for a week, then you start to worry about it. So basically, but the other thing with COVID is that it is a systemic infection. The virus gets in the blood, goes round the body in the blood, and it can infect cells in the heart, the kidneys, the various other organs, probably the muscles. If people come to post-mortem, they don't survive COVID, they die in hospital, the virus is everywhere in their body, everywhere. And it's really a much worse disease than influenza in that sense.
Right. Okay. Well, so I'm a little conscious of time, and I just thought maybe to cap us off, if you might just speak to what you made, just quickly, what you made of our response to this virus, sort of at the level of the nation, internationally, as a scientific community, and how prepared do you think we are for future events?
We were dealing with a completely unknown pathogen, totally new, and we didn't really know the extent of it. And so we had a very, very rigorous public health lockdown policy. After the Ruby Princess event, we really locked down. And before that, we'd locked down to international air travel, I think. But we really locked down very hard. Now, people think that's a very authoritarian response, and that's absolutely true. But those powers have long been legislated in parliamentary governments to deal with pandemics and disease outbreaks. They're in the legislative process.
Right, so they're not a new
For instance,
thing.
in the United States, pardon?
They're not a new thing. They weren't just draconianly brought upon by COVID.
No, if you go back to Venice in the 16th century with the plague, or 17th century, they had these powers. In the United States, for instance, if you're a street person who develops tuberculosis and you're not taking your drugs, they'll lock you up.
Right.
They may put you out on day release, but they will lock you up until you've finished your drug course. And there's the famous case of Typhoid Mary back in the early part of the 20th century, who was carrying the typhoid bacterium. And she was locked up for ages, poor woman, because she always wanted to work as a cook. And as soon as she started to work as a cook, she'd have a typhoid outbreak because she was still carrying this stuff in her gut. And so there are major powers there, just as there are major authoritarian powers in wartime. So those powers were used here, and basically they kept the virus out in the initial phase. So they kept it out before we had vaccines. They kept it out before we had any drugs. So I think we've had about 3,000 people die now. But my calculation is if we just do it on a proportional population basis, somewhere between 40,000 and 70,000 Australians would have died if you compared it with the British results and the American results.
Right.
People don't quote that higher figure, but if you just translate it purely on the numbers of people, basically that's what you were looking at. So I think, I don't know how many people we've had die now, but is it less than 10,000? I'm not sure. So I think a number of lives were saved, but then there's the question, saving lives of older people versus the living of young people, and that's a difficult scenario. And also we kept out the Wuhan virus. It seems that the Wuhan virus, if you had it, is actually suppressing the subsequent immune response to vaccination and or to a superinfection. So it may be a good thing we kept that virus out. But that's just one report so far. So anyway, we did what we did. And I think personally what we should do, and we need academics to do this, that is, we need people who will actually look at the data without any political judgment and look at the data from across the planet. And we look at all the experiments that different countries did, because different countries handled this in various ways. Sweden was always being cited as one type of approach, Portugal another, much more like ours, and so forth. So we look at all those results from across the planet and we say, what worked best? And we ask that question from the point of view of disease incidence and death, from the point of view of economic viability of the population, from the point of view of sociological well-being, and from the point of view of psychological disease, whatever you want to look at. So we need academic economists, sociologists, biomedical scientists, various people, statisticians, obviously, looking at all this data. Now, whether we'll do that or not, I don't know, but I'd love to think we would. And we maybe then would have better clues on how to optimally handle something like this if it comes along again. And I'm absolutely certain it will come along again.
Oh, you are? That's
yeah. We look, there were 2 coronaviruses in the human population before 2000. 5 came across since 2000. What changed? What changed? Prosperity in Asia, where they have live animal and live bird markets, and the amount of international air travel out of Asia. So I'm not pointing the finger at Asia. I'm just saying that
Globalization, in a sense.
globalization gets these viruses around the planet very, very quickly. Here's a coffee cup, teacup. Flu flies. Okay.
Yeah.
So does COVID.
Right. Gets the point across. I think something that a lot of people struggled with in the public sphere was the different responses that were sort of taken in different countries and different states, and it made a lot of it seem ultimately arbitrary.
Yeah, it was arbitrary. It depended on the national legislature, and the national public health community, and so Britain took a very different line from the one we did, and I think we should look at them and say they're not that dissimilar. I mean, we both have a pretty reasonable public health service. Not perfect, but no public health service is perfect. I mean, public health care is just becoming so expensive. So you could look at Britain and Australia and compare those populations. Britain is a very crowded island, but most of us are crowded into big cities. Though, of course, we do tend to live. More of us tend to live in detached housing, I expect. You could look and compare us with the United States. I mean, the United States has a really crap healthcare system for the poor, but they got the vaccines much earlier than we did, and they got the drugs much earlier than we did. So, and you can look at different jurisdictions in the United States too. Washington State, where our youngest son lives, he's a medical doctor in Seattle, locked down pretty aggressively, actually, not as aggressively as we did, but they did a lot of what we did. And they had relatively low incidence, whereas Texas and Florida, controlled by Republicans, didn't lock down hard, particularly Florida. And Florida, I mean, they're nuts anyway, but so you could look at those comparisons.
Right. Well, Peter, thanks so much for your time. COVID is something that in my world seems to appear to have died out, if not quite literally, then at least
psychologically and sociologically, we think it's gone.
Yes.
I hope we're right. And I think it's a good possibility we are. But the real test will be, Lucian, what happens in the northern winter.
Right.
There are just a hell of a lot more people crowded a hell of a lot more closely together in the northern hemisphere than there are in the south, and they're living in cold climate, so they're much more in buildings and inside during winter. So I think if we get through the northern winter and we don't have a nasty shock, I think we can feel pretty happy about it. That it's calmed down a lot.
It's calmed down a lot.
People like Tony Fauci are saying, maybe we'll need an annual vaccination. We'll see. Honestly, we don't know.
Right. Well, I suppose we can hope for the best. Hey,
I think so. Hope for the best, and I think this time, I think we all think in a way that the way this was handled in Australia was probably too hard on young people, and maybe I think we need to really look at what we did and sort of consider how best to handle these things.
I get the feeling that you just might not be able to lock people down anymore now like you could in the past.
I absolutely think that's true. People are totally impatient with what happened here. I think we could be more educated to not so much lock down, but wear masks more, for instance. That would help a lot. Yeah, I don't see why, for instance, I've just been on a tram. And the tram, the thing says you must wear a mask, and pretty much nobody's wearing a mask. So it's not that big an inconvenience to wear a mask on a tram.
People feel like it impinges upon their identity.
On the other hand, if you go to a bar or something and you're with a lot of young people, well, wearing a mask is a real drag.
Yeah, you're not going to be on the dance floor wearing a mask, probably. So
a mask ball.
A masked ball.
A masked ball. There's a ballet, isn't it? On ball and mask.
I'm sure that'd be a nightmare for so many people.
But the masks are actually a bit more elaborate because you could have an N95 underneath. No, I agree. The attraction of the mask is pretty low. But Asian societies, people wear masks all year round in the street, basically because the air quality is so toxic. I mean, if you're in Beijing, the air is at times almost unbreathable, and people wear masks. I mean, they protect themselves.
Maybe us Australians just need to chill out a little bit and get over ourselves and chuck a mask on a little more often than this.
You may say that, but I won't.
No, maybe I shouldn't have. Anyway, when
you can get away with it.
Yeah, when I when I mentioned to a few individuals that I was going to have this conversation, we're going to talk about COVID, and because there's also obviously plenty of other interesting things that you would be able to talk about, and I'm sure we could talk about. But
I can talk for hours about all sorts of things. But basically, in tennis, for instance, I've just published a book on. This was my pre-retirement book.
Oh, really?
Empire, War, Tennis, and Me. Nothing to do with that.
Get a Nobel Prize for tennis history.
No, there's no Nobel Prize for tennis.
Unfortunately. Well, anyway.
Or for skateboarding.
Or for skateboarding. Is that another favorite of yours, is it?
Or mathematics. No, I'm not a skateboarder.
Mathematics. Oh, anyway, Peter, again, thanks so much for having this conversation. COVID seems, though it may seem to have faded in the background, just due to the impact it had on all of our lives.
Well, basically, the Institute, this is our business, basically, infection and immunity. We are an infection immunity institute. So, we work on many infections, not just COVID, and obviously COVID was new. In fact, only one of us had ever really worked much on this class of viruses. She just happened to be at the National Institute of Health in Bethesda when the first COVID hit, the first coronavirus, SARS hit, and they did a lot of research. But the rest of us hadn't worked on these viruses. I published one paper in the whole 500 papers on a coronavirus. And so it wasn't our obsession, obviously, but we'll be monitoring and watching this very, very, very closely for some time, and trying to work out better ways forward scientifically.
I'm sure
there's a couple of experimental vaccines in progress. There's strategies for making vaccines and getting them out much more quickly. And we've just got the biggest philanthropic donation that any Australian institution has ever received of $250 million from a Canadian philanthropist to build a new drug discovery program for virus infections.
That is quite a donation.
So we'll be working on this for a long time, and or on related problems. That's our business.
That's great to hear, and I'm sure we'll all ultimately be better off for it. So,
we hope so.
Anyway, Peter, thanks so much.
Okay, Lucien, be well.